I'm going to discuss section 18.3 and 18.4 here. The structure of benzene was kind of confusing at first. Michael Faraday discovered it in 1825, and all he knew was it was C6H6. And they couldn't do many reactions with it, and the reactions they could do was weird. It wasn't behaving like an ordinary alkene. But August Kekulé proposed this structure in 1866. It's a six-membered ring with alternating double bonds, and it's now described better through resonance theory. One form of benzene has this structure on the left, and we can use our ordinary curved arrows to show an additional resonance structure that is shown on the right. Now, these two structures are equivalent. They have the same number and types of bonds and everything. And one way to draw the resonance hybrid is through the use of this circle within a hexagon. And your textbook author, as well as myself, suggest to you avoid drawing this structure. Even if your professor draws some quick little aromatic rings with a circle, get in the habit of drawing three double bonds, because when we do curved arrow reaction mechanisms, you actually need a bond to attack something, and so it's good to have a line to move from, okay? Now in section 18.4, I would like to discuss the stability of benzene. Benzene is extremely stable. What they tried to do early on was take benzene, which was known to have some kind of unsaturation. It had these double bonds in it, and they tried to treat this with bromine, and there was no reaction at all from this. And that was quite surprising, because if you take cyclohexene, we're all aware that this will react with bromine and decolorize it. That's a form of a test for unsaturation, and you'll get the trans bromide as the reaction product, okay? So that was a big kind of weird thing. Maybe there wasn't double bonds, right, present in the molecule, but there had to be, because you can't really propose much of anything else with the formula C6H6 without drawing some kind of double bonds in it. So if you take cyclohexene, you can also react this with hydrogen gas with a catalyst like platinum or palladium under very mild conditions, you know, room temperature, maybe a little bit warmer, and 1 atmosphere hydrogen pressure, and you'll get the molecule here where you have hydrogen added, okay? And this gives off a certain amount of heat. It gives off an amount of heat of minus 120 kilojoules per mole for that double bond. Now, they took benzene and they tried to do the same thing, and of course it didn't work. So they pumped up the pressure quite a bit, okay? Your textbook gives some pressures here. They use a nickel catalyst. This is at 100 atmospheres, so that's 100 times the atmospheric pressure. And it's not just being done at room temperature, it's being done at 150 degrees Celsius, okay? So this is very high temperature, very high pressure, and what you get from this is cyclohexane. I won't draw all the hydrogens in there. Now, because there are 3 alkenes, they expected to get a certain amount of heat released here of minus 360 kilojoules per mole, okay? But what they got instead was only 208 kilojoules per mole being released, okay? So this is expected. Okay, so they were expecting 360, and what they got instead was 208. And so this substance is really stable by 100 kilojoules per mole or something like that. And that's due to resonance stabilization, okay? So that was very surprising to people when they first found this out, okay? Now, what happens, in fact, is if you take ordinary alkenes and you react them with things like chlorine, okay, you get addition reactions. The chlorine will add to the alkene of your ordinary boring cyclohexene, for example. In the case of benzene, what you actually have occurring is a substitution reaction. So if you add chlorine with a suitable catalyst, okay, they did figure out eventually how to get benzene to react with chlorine, but it didn't react the way they thought it would at first. It substituted that hydrogen for a chlorine, okay? And they got hydrogen chloride as a byproduct, okay? So that's where the chlorine went. One of the chlorine atoms substituted a hydrogen on the benzene, and it spit off that hydrogen in the form of HCl. So this is called a substitution reaction. We'll refer to it as electrophilic aromatic substitution. Okay. And sorry about the spelling. And this does not occur by SM1 or SN2. It's a completely new reaction mechanism. And what you're doing is you're exchanging that hydrogen for, in this case, a chlorine atom, okay? So that's how benzene reacts. It's very different. It's much more stable than chemists had expected, okay? Now, there's something magical about having benzene, because other compounds with more double bonds seem to react just fine. So if you have Cycloocta tetraene, okay, and you treat this with bromine at room temperature with no catalyst, the reaction occurs just fine. On one of the alkenes to give you the addition product, but benzene does not, okay? So there's something important about having a cyclic system and having the correct number of double bonds or total pi bonding electrons in there for this reaction to have superstability, okay? So benzene does not react with bromine, okay? And it took chemists a while to describe the types of molecular orbitals involved and why it doesn't react the way it does, okay? So benzene won't react with bromine, but this one does. So it's not just the fact that you have double bonds and you know their resonance stabilized, okay? Because for the Cycloocta tetraene, I can draw these curved arrows right there on my screen, and I could show another resonance structure, right? Just like I could with benzene. So there must be something else besides just a ring with some double bonds that you can draw resonance. The benzene ring is super resonance stabilized, okay? Let me summarize Huckel's rule very succinctly here, okay? So technically he's Huckel, right? But I just pronounce it Huckel. Now Huckel's rule helps you determine if something's aromatic, anti-aromatic, or just something else, okay? And we're not talking about the smell or taste of compounds, we're talking about the stability, okay? So aromatic things are very stable. Anti-aromatic are extremely unstable. Good luck synthesizing that compound. It's so unstable it's predicted not to exist, in fact, okay? And the third category is something else, neither. Okay? Like H2O or something like that, okay? It can't be classified as aromatic or anti-aromatic because it's just in a completely bizarre, unrelated category, okay? So there's a number of criteria. Criteria number one, okay, is that you must have a ring. Okay, so if I have benzene, this molecule has the opportunity of being aromatic because it's in a ring, okay? This is not cyclic. The way I like to think about this is some train tracks, okay? So if you have those toy train tracks, okay, you can kind of put them together in a circle and put your train on there if it has a motor, and it goes around and around and around and around until it runs out of batteries. If you put your toy train on this kind of train track, it would get to the end of the track and then fall off, and it would not be going around and around, okay? So the first criteria is that the double bonds must be cyclic, okay? The second thing is that it has to be completely conjugated. Another way of stating this is that there has to be a p orbital on every single atom. Now, p orbitals come about from an sp2 or sp hybridized carbon atom. So review your hybridization. This is going to be very important. Okay, so if you have a carbon that has 4 groups attached to it, let's just say like that, this carbon does not have a p orbital on it because it's sp3 hybridized. But if you have a carbon that looks like this, for example, I don't know, it doesn't matter too much what these atoms are on the outsides, that central atom is sp2 hybridized, and that has an opportunity to have a p orbital on it because a pi bond is made from a p orbital. Okay, if we have an atom like this, okay, those lone pair, we have to have some other information about the surrounding area and the structure here, but those lone pairs, it's possible, could be a p orbital. Okay, so sometimes it's a double bond, sometimes it's a lone pair. Okay. And we'll look at that. We'll look at that in a brief moment. Okay, so it must have a p orbital on each and every atom. If we look at benzene, this figure right here is a little bit misleading, but every single carbon atom is sp2 hybridized. So each carbon atom has a p orbital that's sticking up, okay? Let me show you what that looks like with a molecular model. Okay, so here's benzene, okay? It's C6, H6. The white is hydrogen, the black is carbon, we know, and this molecular model represents the pi bonds as these little loops, okay? So there's a pi bond between these two carbons, and these two carbons. This is an incorrect way to think about benzene. Really, there's a pi bond everywhere between every single carbon atom. Let me explain why, okay? Now this model looks really crazy looking, okay? But just focus in, if you would, on just one of these carbon atoms for the moment. Okay, I'll try to hide all the rest of the molecule. That right there is a p orbital. You've got the blue lobe and maybe a red lobe in your textbook. Okay, this is green in this case with this model. Now, a pi bond, remember again, is the orbital overlap between 2 adjacent p orbitals that are lined up side by side. So if I hide the rest of this molecule here, you can see that that is a carbon-carbon pi bond. Okay, you have 2 p orbitals up here that are bonding, and 2 p orbitals, the bottom lobe of the p orbitals are bonding down below. Okay, so we would formally draw a double bond between these 2 carbons, but it's not that simple, because if you look at this molecule, there's a p orbital on every single carbon atom. So is there a double bond here, or is there a double bond here, Or is there a double bond here? It's just arbitrary where you put those double bonds. So that's sometimes why they draw a benzene ring with a circle that shows there's, you know, a humongous molecular orbital, okay? Not just an atomic orbital like a p orbital, not even a pi bond, but a molecular orbital that extends over the whole face of the benzene ring, okay? So there's tons of pi bonding here and here, okay? So there's a p orbital on every atom, okay? And it's cyclic. So far, those are the two criteria that we've discussed thus far that allows Huckel's rule to explain why benzene is extremely stable. So we've discussed there are 4 total criteria for Huckel's rule, okay? The first criteria is that the molecule has to be cyclic, all right? The second rule is that it has to have a p orbital on every single carbon atom. The textbook says that it's continuous or it's completely conjugated, okay? The third criteria is that the ring system has to be flat. In order for those p orbitals to interact with one another, it all has to be flat. If this were somehow bent into a kind of like a boat structure or something like that, then these ring systems these p orbitals in the ring system wouldn't be able to efficiently overlap with one another, okay? So the third criteria is that the ring system has to be flat. And there are systems that are weird, contorted, that are not flat. Let me show you an example of something that's not flat in just a second. Okay, this is benzene. It's as flat as a board. We say it's planar, and this engenders some kind of superstability to benzene, okay? Now, what happens if you have Cycloocta tetraene? So Cycloocta tetraene, remember, is a 8-membered ring, and it has 4 double bonds to it, okay? So this is Cycloocta, right? It has 8 carbons in a ring, and you have 4 double bonds. You can kind of see them here in the picture, okay? So on the screen, there's 4 double bonds here. But if you look at this molecule, it's not flat. It's puckered in a weird way, okay? It's not planar. If I try to force this to be planar, it has a lot of ring strain and it kind of flops back, okay? So this molecule is cyclic. It's completely conjugated, meaning there's a p orbital on every single atom in the ring, but it's not planar, so this is not aromatic. It does not have humongous stability that the benzene does. And so it reacts with bromine at room temperature to give you the addition product, because this alkene isn't in efficient electronic communication with the other ones in this aromaticity, okay? So let's summarize now what these 3 things are. You have to have a cyclic system, okay? It has to be completely conjugated. And we'll go into this in more detail in a bit, but you have to have a p orbital on every single atom of the ring, of the cyclic system. The third criteria is that it needs to be planar. It needs to be flat, right? Okay? And these are Huckels criteria, okay? Now, here's where the interesting situation arises, okay? If those 3 criteria are met, then you start counting the pi bonding electrons, or the electrons in the pi bonds, in the pi system. If the number of pi bonding electrons are 4n plus 2, that's going to be aromatic, okay? 4n is going to be anti-aromatic, okay? And if any of those rules are broken, rule 1, rule 2, rule 3, rule 4, you know, some other multiple of, you know, it doesn't fall into the 4, you know, as an odd number of electrons, for example, it's going to be something other, okay? Now let me explain to you what the 4n plus 2 is, okay? N is any integer. So 4 times 0 plus 2 is equal to 2 electrons. We'll look at systems like this in a second, but things like this have 2 electrons, okay? So that's a single pi bond. There's 2 electrons there. It is satisfying the 4n plus 2, so we say that this molecule right here, I know it has a charge, it looks weird, we say that that is aromatic, okay? 4n plus 2, let's look at benzene, okay? 4 times 1 plus 2, right? N can be 0, 1, 2, 3, any whole number. That's 4 plus 2 is 6, okay? And if you add up all the electrons in benzene, each pi bond has 2 electrons, so that's a total of 3 pi bonds, 2 electrons each, that's 6 electrons. So we say benzene is aromatic, okay? Another category of aromatic rings is polycyclic aromatic hydrocarbons. These are components of forest fires, diesel smoke, soot, cigarette smoke. They're usually, some are carcinogenic, they're usually toxic, and they're a component of smog. It's not really good. So polycyclic aromatic hydrocarbons. Polycyclic means more than one ring. So let's look at naphthalene. And we want to identify how many total electrons are in this molecule. So each pi bond is 2, okay? So you count all those up, that's 10 electrons. And so we want to see, is there 4 times some number plus 2 equal to 10? And the answer is yes, okay? So these are all examples of aromatic compounds, okay? If we have a structure like this, without making a model of it and thinking too hard, we know it's a ring. Is it flat? Let's assume. There's a p orbital on every atom because there's pi bonds there, right? And we want to count up the total number of electrons here. 2, 2. Now, this is actually a multiple of 4, right? Where n is equal to 1. And what that means is this molecule is anti-aromatic. Okay? Now, if aromatic means it's super stable, anti-aromatic means that it's super reactive, super unstable. In fact, this wasn't synthesized until the 1970s. People couldn't figure it out. They tried to make it in many different ways. And they finally figured out a very creative way to make it and study it before it decomposed. Okay? It reacts very quickly. You can't put this in a bottle. It's synthesized at ultra low temperatures and studied spectroscopically and things like this. Okay? So that's an example of an anti-aromatic compound. Okay? Let's look at, so that's the brief overview of Huckel's rules. There's 4 criteria. Remember, if you have something like this, we are not going to be counting electrons necessarily because these double bonds aren't all in a ring. They're kind of extending through the molecule, okay? So we would call this not cyclic. So we would not say this is anti-aromatic. We would not say this is aromatic. We would say this is other. Okay, let's look at another one. Something crazy like that, right? Think about these as train tracks. If you put your train on it, you might be able to go that way or this way or, zigzag a little bit, but not go around and around and around. So this is something that's other than aromatic, okay? What if we have something like this? you might not be able to locate a good resonance structure for this. But let's just count up all the, so first of all, we're assuming this is flat. We can see how every atom is sp2 hybridized. There's a pi bond on every carbon, and there seems to be a series of rings, okay? And perhaps if you had if you had the right train track, you know, it could go around and zigzag in a figure 8 kind of through this whole structure. So let's count now all these electrons: 2, 4, 6, 8, 10, 12, 14, 16, 18 electrons, okay? And we'll see, is it a multiple of 4n or 4n plus 2? So I could see that it's 2 more than 16, right? So 4 times 4 plus 2 is equal to 18. So that's a magic number there. I would say that this structure right here is going to be aromatic, okay? So that's a little bit about how to determine and count electrons for various things. I hope you don't get too confused about the N. N does not stand for the number of rings. N is just an arbitrary mathematical number, and you count your real live molecule that you have, and you see if it's a multiple of 4n plus 2 or not, okay? Okay, I want to talk about aromatic ions. Now, this is the concept I want to introduce you to, okay? I'm just going to put, well, let's just put a carbon here. So if you have lone pairs next to a pi bond, we're going to call it conjugated, and those electrons are in a p orbital, okay? Now, I rarely write anything out word for word, but this is like very, very critical, okay? So when we look at structures, we're gonna see lone pairs here and there and so on, and we want to look next to it to see if there's a pi bond. If there's a pi bond next to that lone pair is going to be in a p orbital, okay? Rule number 2, and this is all there is, if you have lone pairs that are on an atom that already has a pi bond to it, those lone pairs are not in a p orbital. Why are they not in the p orbital? Because there's a pi bond there. It has the p orbital making that pi bond. So those lone pairs are actually twisted orthogonal to it, okay? So those lone pairs are not part of the p orbital, okay? So let's look at cyclopentadienyl anion. Okay, this is a negative charge. So let's take cyclopentadiene. Let's treat this with sodium hydroxide in an acid-base reaction. I keep the same color pen, I guess. So we're removing one of those hydrogen atoms. And this right here is called the Cyclopentadienyl anion. And if you count the pi bonding electrons, you of course have a pi bond. So there's 2 electrons in that pi bond. There's 2 electrons in this pi bond. And there's 2 electrons on that carbon atom because, once again, rule number 1 that I'm stating is that those lone pairs are next to a pi bond. So it makes them conjugated and it makes them in a p orbital. Let me show you a molecular model, and then we'll do some curved arrow resonance with this. Okay, it's kind of hard to show you these things with models that aren't too dynamic, but here's cyclopentadiene, okay? We've got this pi bond here, we've got this pi bond here, so there's a total of 4 pi bonding electrons. This carbon on top is sp3 hybridized, it has 4 carbons attached. So this is not aromatic, it's something other, okay? We wouldn't classify it aromatic, we wouldn't say it's anti-aromatic, because it's not completely conjugated. There's no p orbital on this carbon that allows there to be pi bonding electrons that can be delocalized in a very cyclic manner. So when sodium hydroxide comes in and deprotonates one of these hydrogens, we could possibly get a p orbital on that atom that would be in a p orbital. Why would that lone pair be in a p orbital? Well, let's just draw it like this, okay? So here's our cyclopentadienyl anion. We've got the double bond still, and on this carbon we have a formal -1 charge, okay? So we've removed one of the hydrogen atoms. So now you can see from the side view that we've got a lone pair existing in a p orbital. So there's 2 electrons in this p orbital, 2 electrons in this pi bond, and 2 electrons in this pi bond, for a total of 6 bonding pi electrons. So this is kind of like isoelectronic with benzene. So this p orbital is in communication with the other pi bonds in the system. Here, look at this model. We have this nice, pentagon, okay, 5 carbons in a ring, and each of these carbons has a p orbital now. Now when you look at it like this, it looks extremely symmetrical. It looks almost like that weird thing I was showing you with benzene. Instead of 6 carbons, it's got 5 carbons and a -1 formal charge. So that's cyclopentadienyl anion. It's cyclic, planar, completely conjugated, and it has the requisite number of electrons to make it aromatic. So getting back to this structure, organometallic and different chemists might draw the cyclopentadienyl ring like this. Instead of the double bonds and the 2 dots and the minus charge, they might draw a circle and then draw a minus in the middle of that circle to represent the formal charge. Okay, but we won't do that. I'm just showing you that. Now, what we can do with these electrons here is delocalize them, okay? And we can draw resonance structures So that's one. You can see how it goes to every other carbon. So here's the negative charge now. And so if we show the classic kind of movement of electrons using curved arrows there, we can show another resonance structure that's going to look like this. Okay, the double bond's going to move here, there's 2 electrons there, and there's a formal charge on that carbon now. And if we keep moving this charge, hopping through the pi bonds, we can see how the double bond will now appear there, and the formal charge is now there. So none of these are the same yet. And if you keep moving this around, you get the 5th structure here, okay? So let's just call them 1, 2, 3, 4, 5. And if I take this 5th structure and I try to move this, these lone pair electrons up here, I'll get back to the starting structure again, okay? So cyclopentadienyl anion is this perfectly conjugated system with a hydrogen on each of the carbon atoms. And the negative charge is in each of the 5 carbon atoms, okay? So it's very delocalized. The charge is delocalized. Okay, that's the cyclopentadienyl anion, okay? Now, Another one is the, what's it called? The tropylium ion, I think it's called. Tropylium cation, okay? So the tropylium cation, I'm not sure how it's made. It's probably made through an SN1 or something like that, but it uses a 7-membered ring. And these are harder to draw. I kind of have to draw it slowly like that for my rings to work out. Okay, so let's review here again. Remember that if you have a carbon-carbon pi bond, we say that each one of these carbon atoms has a p orbital. Okay, when you have a carbocation, as we saw with the SN1 reactions and stuff like that, we said it was described by a p orbital, and you know the nucleophile could come in from either face, right? So it's a planar type of creature, so that's a p orbital. Okay, so remember again the criteria for aromaticity. You have to have a ring. This is definitely a ring. You have to have a p orbital on each and every carbon atom, and there's a p there, and you know there's a p orbital on every single carbon atom. Great. Now you have to count up the electrons. 2, 4, 6, 6 electrons. There's 0 on the top carbon, so there's 6 electrons. And so that right there satisfies 4n plus 2, where n is equal to 1. So that's aromatic. Aromatic. Okay? This molecule, this ion forms during mass spectrometry. If you've been through chapter 15, it can also be produced by you know, SN1 reactions or things like that. So it's super, super resonance stabilized. Now, we can draw a resonance structures by moving the pi bonds like so. I'm just going to do this once because it's pretty hard to draw these 7-membered rings. Okay, and so it looks like the positive charge is moving, but actually it's the electrons that are moving. The electrons are smeared all around that ring system on the top face and the bottom face, and the positive charge is 1/7 on each of the 7 carbon atoms, okay? So that's just one resonance structure, and you'll see how the positive charge alternates, okay? Every other carbon, but if you move it around the ring, you'll be able to draw 7 different resonance structures, okay? So that's the tropylium ion. Now, when you're counting different molecules to see if they're aromatic or not, you have to be careful of how many electrons you're counting. Okay, so if you have a 6-membered ring, you can have funny stuff that you can draw. Okay, so let's just look at these crazy looking structures and let's practice counting for the 4n plus 2 system, okay? So let's assume first of all that all of these are cyclic. Yes, they are. They're planar. So each of these molecules here have a p orbital on every single carbon atom because a carbocation is a p orbital. And remember what we said, if there's a lone pair next to a pi bond, that's going to be in a p orbital, okay? So each one of these molecules here are cyclic, completely conjugated, and we just need to count the total number of electrons. In this first molecule, we have 2 electrons in total that make up that pi system. Remember, there's no lone pairs in a carbocation. So that satisfies the 4n plus 2, right, where n is equal to 0. So we would say that this first molecule here is aromatic, okay? This second molecule here, there's no charge to worry about, but there's a total of 2 pi bonds, so that's 2 electrons each, so that's 4 electrons. That satisfies the 4n, where N is equal to 1. So we say this one is anti-aromatic. This third molecule here, there is indeed a p orbital on every atom. We just need to count things up, and we see that we have a total of 6 electrons. Okay, 6 electrons, just like benzene. So that satisfies the 4n plus 2 rule, where n is equal to 1, and we would say this molecule would be predicted to be aromatic. It would be a +2 cation. Okay? Our next molecule, Cyclopentadienyl, we've discussed previously. There's 2, 4, 5, 6 total bonding electrons. So just like benzene, that's going to be 4n plus 2 aromatic. Okay, where n is equal to 1. Our next molecule here, we have a total of 2, 4, 5, 6, 7, 8 electrons. So that satisfies the 4n, where n is equal to 2. So we would say this one is anti-aromatic. Okay, so you have kind of a brief kind of view of things so far, and now we'll start looking at heteroaromatic. Heteroaromatic rings are aromatic rings that have nitrogen, oxygen, or sulfur within the six-membered or five-membered or whatever ring system that you have. Okay, the first thing I wanted, okay, so I've highlighted in yellow here the things we really need to remember, and this goes back to my rules 1 and 2 about how do you know if lone pairs are a p orbital or not. Okay, this first molecule here on the left is called pyridine. Pyridine is aromatic and contains 6 pi electrons. We count 2, 4, 6. We do not count the lone pair on nitrogen because it's not in a p orbital. The p orbital is the pi bond, not the lone pair. Let me show you a few molecular models of this so you can see what pyridine looks like. This is pyridine. It looks a lot like benzene with your 3 double bonds. A double bond here, here, and here. It's a nice 6-membered ring. It's planar. The only difference is that we have nitrogen here and there's a lone pair. The lone pair is not in the ring system that make up the pi bonding electrons of the molecular orbital. Okay? The lone pair is sticking out that way. So it's a train track that's off in somebody's toy box. Okay, it's not part of the system here. Okay, let's look at this molecule here. So here's pyridine. If we kind of look at it, I'm holding on to this nitrogen atom here, and you can see that you have those all those top lobes of all the p orbitals that make up the 3 pi bonds up here, and these are the bottom lobes of all the p orbitals that make up the pi bonds down here. I don't have enough of these lobes, so I'm gonna have to steal one to kind of highlight where this lone pair is sticking on the nitrogen. This nitrogen is sp2 hybridized. The nitrogen's sp2 hybridized, which means that the lone pair is in an sp2 hybrid orbital. You see, this is the p orbital that's going up and down in our orientation here that makes a pi bond with the adjacent carbon atom. Okay, so that's the pi bond that's being made there. This orbital that's sticking over here is in the plane of the molecule. And so if I look at this nitrogen atom now and I twist it this way, you can see how this lone pair right here that I'm holding on to, this bond to this carbon and this bond to this carbon are forming a nice triangle of an sp2 hybridized nitrogen atom. Okay, the p orbital of the unhybridized nitrogen is what's forming a bond, a pi bond to the other carbons in the ring. Okay, so that's pyridine. I think this model is maybe a little bit easier to view. So if nitrogen is forming a pi bond to a carbon atom, it's those p bonds or the pi bond, the p orbitals or that pi bond that we're counting. We're not counting the lone pair that's not part of that loopy feature there that we have in this molecular model. Okay, so looking back to this heteroaromatic ring system of the nitrogen, I'm just going to highlight maybe with red here that these lone pairs right here are not p orbitals. They're in an sp2 hybridized system. Why sp2? Because the nitrogen in this Lewis structure that I have is forming a nice triangle with these three groups. Okay, the lone pair is pointing up, the carbon is pointing to the left, the carbon is pointing to the right. So we say that that's sp2 hybridized, and this is an sp2 orbital. Okay, the p orbital is coming in and out of the board, and it's that yellow line, it's that pi bond. Okay, so that's pyridine. Okay, pyridine is an aromatic ring. All right, our next one is called pyrrole. Pyrrole, spelled with two R's. Let me fix that here so I don't lead you all astray. Okay, this is the pyrrole ring system, and this has 6 pi electrons. It's also 4n plus 2. It's aromatic. Why? Well, we're counting these 2 electrons right here. We're counting these 2 electrons right here. And now we're counting these 2 electrons on nitrogen. So why are we counting those lone pairs on nitrogen? Well, because they're next to a pi bond, so we count them. If they're next to, I tried to highlight it here in purple, if they're next to the pi bond, you count them. If they're on the pi bond, you don't count them. Okay, so this has a total of 6 electrons. It's 4n plus 2. It's aromatic. Okay, let me make a molecular model of this and get back to you and show you what that looks like. All right, so in my hands, I've got the pyrrole molecule. So this nitrogen should really be flat, but this model is incorrect. Okay, so the Bacon model kit, it doesn't have the correct thing. It kind of looks like this hydrogen is pointing down. But for the blue and the black, they're all in a plane here. Okay, I'll just kind of hold my hand on this part. And if you look at it sideways, you can see the 2 pi bonds, okay, 2 pi bonds, and you can't see the lone pair, but you know, I'll use this little peg here and I'll jam that in the nitrogen atom and we'll count that. Okay, so there's 2 electrons here, there's 2 electrons from this pi bond, and then there's 2, right? The lone pair is 2 electrons, so that's 2, 4, 6 electrons for the pi bonding electrons. Okay, so it's a planar molecule, it's aromatic. It does have a hydrogen here, okay, because nitrogen normally has 3 bonds. Okay, so there's a bond, a single bond, a single bond, and a single bond to hydrogen. So that's why we have the hydrogen here on the nitrogen atom, so that the nitrogen has 3 total bonds to it. And we'll get to this crazy looking structure here. So I'm holding on to this blue, kind of light blue, atom, and that's the nitrogen atom. Okay, so this is the nitrogen, and we got carbons on the other positions. And if I hold it like that so you can't see the orbitals too much, you can see it's a nice 5-membered ring, and there's CH bonds, right, for each of these hydrogens, and then there's the NH bond, okay? So it's C4NH5, all right? When I twist this sideways, now you can clearly see how this nitrogen atom right here that I'm pointing to has a beautiful p orbital on it, and that lone pair is delocalized, right? Not just on both lobes of this p orbital, but that lone pair is delocalized with all the other pi bonding electrons on the top face of this molecule and the bottom face of this planar, completely conjugated 6-electron aromatic molecule. Okay? Okay, let's do one last thing here before we move on. So it's really important to know which lone pairs to count, and I'll highlight those in yellow. Remember, if it's next to a pi bond, you count one and only one of those lone pairs. If it's on a pi bond, do not count it. So, of course, and we count pi bonds, okay? So let's move around the ring system in a clockwise way, more or less. So we count this pi bond. This lone pair, pick only one of them, is next to the pi bond. Here's a pi bond, and pick one of these lone pairs, which is next to the pi bond. Count up those in yellow, 2, 4, 6, 8, 8 electrons. This is 4n, this is anti-aromatic. Okay, how about the next one? We count these 2, okay? These electrons are on the pi bond. It's on an atom that already has a pi bond to it, so we don't double count. We can't count, okay? If there's a p orbital, there can't be another p orbital in the same location. We count this one, but not these, because that's also on an atom that has a pi bond. So 2, 4 electrons, that's anti-aromatic. Okay? This next hetero, oh, I forgot to draw some lone pairs on the nitrogen atom there. Now, if you're presented with molecules without lone pairs, go ahead and add them in, but know which lone pairs to count. So we count the pi bonds, okay? We count electrons that are adjacent to the pi bond, just one lone pair per atom that's adjacent to the pi bond. We don't count lone pairs that are on a pi bonded element. So 2, 4, 6 electrons, this is predicted to be aromatic. And I think this is an oxazole ring system, or isoxazole. I forget the names for all of that. So anyway, this is aromatic. Okay. Over here, we've got 2 pi bonds. Okay. These lone pairs are on this atom that has the pi bond, so don't count that. We count these lone pairs because they're adjacent to a pi bond. So 2, 4, 6 electrons. This is aromatic. Okay. This last type of molecule is present in histamine. It's histidine. It's an amino acid present in our bodies. So that's it for aromatic chemistry. I hope you understand how to identify if something satisfies Huckel's rule or not, if it's aromatic, anti-aromatic, or something else. Okay? Thanks for watching.